Howdy, everybody. Good morning, slightly good afternoon. Just as Buck said, thank you for attending. I will summarize the question and answers afterwards and send out everybody who attended a summary of them. I'll combine that with part one so you have them all in one spot. And then also we can issue 1.0 PDH credits. A lot of people have already requested them, so just give me a couple days as the requests come in and I'll get those out to you. All right, so let's get started. Today, just the agenda, want to review rooftop units. My objective for today, just application considerings, best practices when you are designing large rooftop units. We'll continue on introducing the next generation of customizable options. We'll focus on AAON's new RZ large rooftop unit. And then lastly, we'll review some customizable applications for humidifiers and energy recovery, et cetera, like that. All right, so just a quick review. Rooftop units, they're great. HVAC in a box. You get controls, filtration, your cooling with the DX refrigeration system, different options for heating, and then you have all your three air streams covered: outside air, supply air, and return air. Rooftop units could be classified into three broad categories: unitary or package units, smaller side, less features. Next, you have applied, where you have a little bit more options available, a little bit more heavy-duty engineering features. And then the last one I'm trying to push today is a new customizable classification or category of rooftop units. And then just drew a couple of arrows there because the blending of each of the different categories, they blend with each other. Just the HVAC industry is moving towards more customizable options. People are realizing the benefits of the higher quality, higher end equipment. And then just the new customizable units do come in larger capacities. They have more options, higher efficiencies, and then more accurate and better comfort control. So just an evolution of large rooftop units. Just over the years, improvements that they've made, they've become very large in size. They've greatly increased their efficiency, mostly due to the use of VFDs on compressors as well as fans. Indoor air quality, where you have increased your filtration effectiveness, you can increase the amount of outside air allowable through these units. And then the next items are controls, technology of components, as well as applications. From a controls perspective, the rooftop units, just like the HVAC industry in general, has transitioned from electromechanical to DDC. There are much more sequence of operations available. Technology of components is essentially going from constant volume equipment or components to variable speed, allows more accurate control. And then in terms of applications, large rooftop units were typically only used for large open spaces or for office buildings. But just over the years, they've greatly increased their availability or just applications that they could use for with makeup air, DOAS units, as well as in the health science industry. And then, as I said in part one, these four items here are all kind of interlocked together. If you have an application with a health science, you could provide much higher filtration, you can provide much more accurate capacity control, et cetera, like that. And then just today's objective is trying to get you to use more customizable rooftop units on smaller tonnages, and then also along with for more applications. All right, so considerations and best practices. This is a summary from the first slide. We have a large customizable rooftop unit shown in the upper right. You have your outside air mixing with your return air. It then comes out as supply air after it's been heated, cooled, and filtered. Typically, there's VAV boxes or air terminals on the discharge or on the supply air side. You do have a service vestibule for ease of maintenance. The benefits of these systems are it's HVAC, once again, in a box, design flexibility. From an engineering perspective, a lot of the heavy lifting is done at the factory. They are energy efficient. They can be provided with high filtration. They have an option for hot gas reheat for dehumidification control. And then ease of complicated controls, all the sequence of operations and algorithms have already been figured out at the factory. Just when your technician goes for startup, he just chooses, outside air, VAV, constant volume, et cetera, like that. And then from a maintenance perspective, these units obviously are on the roof, so that's an advantage that it's not in the space. And then they are centralized in terms of, instead of having multiple locations. Disadvantages of large rooftop units, you just can't get away from it. There's a lot of airflow, so you end up with large ductwork. That means, large ceiling spaces, also for duct shafts. And then also too, the weight of the rooftop unit and the noise. I'm going to talk about these two things here next to try to mitigate or just get a better understanding of what you're faced with when you're designing large customizable rooftop systems. All right. So from a weight perspective, there's two items. You have support as well as rigging. What I did was I went back and looked at, okay, what's the approximate density or the weight in pounds per square foot of rooftop units? I went back on previous jobs that I had done with AON units, where the sizes were less than 40 tons. The range was from about 35 up to about 60 pounds per square foot. And then with the new RZ, I just looked at a 90 and 160 tons, a couple of different options. The range was in the 40 to 50 pounds per square foot range. It's about the same, a little bit on the lower side, so you are getting some economy and efficiency of scales. And then just on the drawing on the, the picture on the right, instead of a rooftop unit on a roof curb, obviously a lot of times these are installed on a support steel that will, the legs will tie into the structural steel down below a little bit more accurate or a little bit better versus a roof curb. From a support perspective, over the years have found out that if you have a rooftop unit that's longer than 15 feet long in either direction, you must account for the weight of snow drifts. This is a requirement per ASCE number 7. So there's a threshold of a rooftop unit. If you're above 15 feet, you have to beef up your structural steel versus below that. So AON has a D cabinet unit. This is without a wheel. It goes from 26 to 70 tons, and these units are less than 15 feet long. And then just on a couple recent jobs within the last year, these AON units and this footprint requirement has allowed me some flexibility on a couple of designs. The first one was looking at, it had a 120-ton load. We ended up providing 2 60-ton units versus 3 at 40 tons. We were able to lower installed cost. And then the second job was 80 tons, and we looked at 2 40-ton units versus 1 80-ton. Just the overall cost of the project ended up being the same, just because the 2 40-tons units did not require this additional structural steel due to the weight of the snow drifts, the snow load. From a rigging perspective, once again, these units are large. So here's a 90-ton unit with one piece. It's 21,000 pounds. Most manufacturers do have an option where you can split these units into 2 sections. So in this example here, there's section 1 with that weight, section 2 with that weight. Maybe this has an opportunity to lower your crane cost, the size of your crane based on your weight as well as the length of your pick. And then the other item that it was advantageous looking at this was when you split the unit in this configuration here, section number 1 had all of our refrigerant piping factory installed. We didn't have to do any splits in the field. And then just a similar example on a 160-ton unit, you can just see once again splitting the unit from 1 piece into 2 reduces our weight of each section. From a sound perspective with large rooftop units, first I'm going to look at ductwork. Just when you are designing the ductwork, especially around the supply connections to each of the units, follow SMACNA guidelines for transitions, for your elbows, the throat of your elbows, your turning radiuses, et cetera, like that. Some other things to consider is providing acoustic insulation on the supply and return. Just as a sidebar or comment, just seems like over the years, this design feature has been reduced in usage. I'm guessing that's just because of an indoor air quality association. On the supply, we can stiffen the ductwork, excuse me, by adding additional supports, maybe increase our gauge of ductwork. We can provide flexible connections. Just where the ducts do penetrate the roof, you want to make sure you seal around those openings so there's no line of sight, that sound can transmit through. And then just down below, you should consider where your locations of diffusers and grills are versus the rooftop unit. Once again, want to try to eliminate any line of sight situations. And then if you do have a return air plenum, you should consider adding a little bit of ductwork on the unit itself, and then maybe at the air outlets into the ceiling, putting in some type of elbow or T or Z-shaped piece of just transition ductwork, once again, to try to eliminate any line of sight problems. From a locations perspective, if you can locate the unit away from occupants, that's always a bonus. Near structures with no bounce, what I'm referring to is you want to try to locate these units near your structural steel. You don't want to put them mid-span. That mid-span also often has a problem with vibration and support, et cetera, like that. You can provide vibration isolation curves, a couple pictures there. And then the other little tidbit or trick is in their roof space beneath your compressor and your fans, where that's where your sound is being generated. Inside the roof curve, before the unit's obviously installed, you can put some type of sound battening or sheetrock. What you're trying to do is put some kind of not thermal mass, but just mass, so you can reduce that low frequency sound transmission. Other thing that's critical or you have to be considerate about is your fan selection. You have to be worried or just concerned about your minimum operating point. Here's an example of two fans that were available, about 10,000 CFM, 4.5 inches of static. Fan number A, if you selected this unit and you plugged in your VAV operation, you're only allowed about 5% turn down before you went into your surge area on the curve, on your fan curve. And then selection B looked at this one based on the different wheel sizes, et cetera, like that. This one here, you're able to turn down to from 40% versus 100%. So that one was much more attractive versus fan A. Other option, everybody's probably very familiar with this, compressor sound blankets. Removable, once again, they have some type of mass to them to try to reduce the low frequency wavelengths. Other considerations for reducing the sound is in customizing the unit. You can put in a supply air plenum right before your discharge connection. Let's swap the position of the fans for a blow-through configuration, so it's a little bit further away from that supply air connection. With the option boxes that I'll talk about later, you can provide sound attenuators. Another option that's come up the last couple of years is low noise condenser fans. Here's a blow-up view of the new condenser fan. It consists of 3 components. From left to right, you have your fan blade with your outlet on the trailing edge to reduce the sound. The center black piece is a diffuser support. It ends up pre-swirling the air, and then it also directs the noise upward instead of horizontally. And then the last component in the blue there is your EC motor. These 3 components end up providing more CFM at a lower RPM, and that translates into quieter operation, as well as making it more efficient. Next, for building consideration, we want to talk about or just consider building pressurization controls. Typically, you want to maintain an approximate positive pressure of about 0.05 inches, plus or minus, et cetera. To do this, you want to try to minimize the amount of infiltration of untreated air from a thermal and humidity standpoint, as well as indoor air quality. Now, this is easy to do at your design conditions, but when you have VAV operations where your supply air, outside air, and return/exhaust air is all changing, it becomes much more difficult. And also too, when you have economizer where your outside air increases, this is also another situation where you have to be careful about building pressurization control. The two main methods to do this are with power exhaust fan system or a return air fan system. Typically, because of the size of these units and the size of the airflow, you typically can't use barometric relief systems for this, for these large rooftop units. Let's go through explaining just the two differences between power exhaust and return fan. Here we have a cutaway view of a rooftop unit. You have your outside air on the left mixing with your return air. It then travels to your supply fan. What you'll have is in the lower left-hand corner is an exhaust air connection to the outside. We have a modulating power exhaust fan. As your outside air damper changes the position and changes the airflow, your power exhaust fan will intermittently turn on and turn off. Two ways to control this are with a simple way is just based on your outside air position versus your power exhaust fan. As your outside air position opens to a greater percentage, your power exhaust fan will then modulate on. It can be controlled either by a VFD or a lot of times it's just simple on-off operation. And then the second method to control the power exhaust fan is we're going to modulate the power exhaust based on the differential pressure between the indoors and outdoors. All right. Next is a return fan. There's two methods to control the building pressurization control for this. The first one is using static pressure as well as your fan system. We have our same outside air, exhaust air, return air, and supply air considerations or airflows. But what we're doing is our return fan is installed in series with your supply fan, and then the supply fan runs, the return fan runs continuously with your supply fan. One way to control this is by installing a Ddc controller and you have your VFDs on your fans. You would have a duct static pressure sensor for your supply air. This would be approximately 1 inch to 1.5 inches set point. And then as your static pressure changes, your supply airflow changes. And then essentially what your Ddc control system does is it tries to keep the same proportion of return air versus outside air through all this different operation as the supply fan, as the supply air CFM travels up and down. This is one way to control the return fan. A second way is to use airflow measuring stations. These are typically more common with return air fan systems. So I try to show it smaller, could be with power exhaust fan systems. What you'll do is you'll measure your outside air, your supply air, and then whether you have return air or exhaust air, you measure one of them. And then each of these three airstream requires three components. First, you have a measuring device. You have a transducer that's going to convert the static pressure signal to an electronic signal, and then you have your controller. HC&I represents Paragon. The pictures down below just depict the three components. On the left, you have your measuring devices with pitot tubes. In the center, you have your transducer, and then on the right is your controller. And then just realize that for each of these three airflows, you have each of these three different components. So what Paragon has come up with is a better way to do the airflow measuring stations. With the controllers, you have a lot of difficulty with locating them. These typically have to go in a controls department. With three controllers, they take up a lot of space in terms of the physical size of the controllers as well as the access that's required. In addition, each of these controllers requires a power connection as well as a backnet connection. So recently, Paragon introduced a multi-trans MTSE, multi-trans smart ecosystem, where they've combined the three items into one, three airflows into one device. So now we only require one power connection, one backnet connection. Obviously, the space required is much smaller. And then another benefit of this new system is that in addition to measuring airflow, they can also measure up to 4 differential pressure readings across filters, energy recovery wheels, et cetera, like that. All right. So a summary comparing the two different building pressure control systems, your power exhaust versus your return air system. Typically, the power exhaust fan system is lower in first cost. I'll say that the power exhaust system, because of that lower first cost, is typically the one that's more commonly installed. From an energy perspective, typically the power exhaust system, because it cycles on and off based on the outside air flow, typically has lower energy uses versus the return fan that's constantly operating. And then if you do have a duct system, especially your return air duct system that does have a higher static pressure, you should use your return air fan system. And then if you do have a critical application where you have to really accurately monitor airflow or as well as pressurization, you should use a return air fan system. All right, next we'll talk about some of the features of AAON's large RZ unit, just the direction that the industry seems to be taking. These 5 items here, I talked about the fan array, service vestibules, and specials in part 1. So today I'm going to talk about the different refrigeration systems as well as a few other options, and then go through a little bit more details and options available with the factory installed option boxes. Just manufacturers are transitioning to variable speed compressors. A picture of a variable speed compressor there on the right with the VFD. Advantages of higher part load efficiency, just really probably being driven by code. Accurate capacity control. The disadvantage is that they typically have higher first costs, and then you do have to just be careful about the amount of turn down. They typically don't have as much turn down as a digital scroll compressor. And then you also have to be careful about oil return, or just that's really taken care of within the refrigeration systems control system. Next, for the evaporator coil, you have customizable for different face areas. There's a couple different pictures there. Advantage of that, it's going to offer you some flexibility. If you have the ability, you can oversize your coil with a larger face area. That's going to result in lower face velocity, lower air pressure drop. Usually items that have a lower air pressure, airflow through them stay cleaner for longer. You'll have extra capacity. And then just everybody's aware of recent the COVID and the ASHRAE task force, where they said, if you can increase the amount of outside air in your existing systems, that is a good idea. So this is a perfect example of maybe putting in a little bit of future capacity when you're designing something today. From a circuiting perspective, the manufacturers are changing to a full face area, where they won't have any untreated air bypassing. This results in better capacity control and then easier to control and stage. Just manufacturers are transitioning on the coil construction from aluminum copper to aluminum microchannel. This is very common in condenser coils. There's a cutaway view of the microchannel. Pretty sure everybody's really familiar with these already. Just the advantages of the microchannel is they're lighter in weight versus the aluminum copper. They have better heat transfer. There's less refrigerant charge, which is always important, especially on a lead project. And they also typically have lower air pressure drop versus a 4 or 6 row aluminum copper evaporator coil. Next, we're going to talk about the hot gas reheat, how the system is transitioning to a new style. Everybody, once again, is familiar with hot gas reheat. It's used to dehumidify and cool the air, and then you're using the refrigeration system to reheat the air to provide neutral air conditions. Benefits of a rooftop unit, its package. This satisfies the code that you're not simultaneously cooling and heating. Pre-engineered, low cost. Applications, not just for places with a high latent load like gyms and restaurants, or facilities that have tight humidity and RH requirements. A lot of times you're just seeing these, automatically included in your selection. And then just once again, the industry, the next generation of the industry, there's a lot of grow rooms. Saw something in New Jersey that they just, passed it. But these grow rooms or indoor agriculture have a requirement for high reheat requirements instead of neutral air. And this new hot gas reheat system that I'll talk about dovetails nicely into that. So previously, limitations with hot gas reheat was accurate capacity control. A lot of times these were just designed initially as on-off systems. Just they've improved greatly in the last couple of years by providing modulating controls with modulating compressors. The other limitations or items that you have to be careful about is generating enough reheat capacity at part load conditions, part load cooling conditions. And then, as I mentioned before, with indoor farming, applications that have leaving air temps greater than neutral air has been a problem. So here's the psychometrics, simple psychometrics of hot gas reheat. You have your cooling system starting at A67. You're running through your cooling coil down to about 55. And then you have a second reheat coil that reheats the air sensibly from 55 up to about 70 or 75. Now, when you have part load, just realize part load cooling is now your mixed air temperature entering is not at 8067. It's somewhere much closer to that 55. So a concern with hot gas reheat systems is oftentimes these are only installed on one circuit. And then at part load conditions, sometimes there's only one refrigeration circuit operating. And then the other thing just to consider too is that typically these part load cooling conditions occur when the ambient temperature is lower. So instead of being 95 or 90, it's in the 70, 65 degree range, et cetera. So what ends up happening is our refrigerant temperature is that we have available, it's colder than if it's used when it's 95 degrees out. So here's a simple schematic just explaining or showing a series hot gas reheat. Not going to really go through the controls, but let's just start with our space, the big green box in the upper right center. We have our return air entering our blue evaporator coil. It then gets cooled. That cooled air then goes through our red reheat coil and gets reheated and gets distributed to the space. On our refrigeration circuit, we have an evaporator. Upstream, we have the expansion valve. We have the compressor. It's the brown, looks like a bowler hat, maybe something from the Beatles, Sgt. Pepper kind of thing. And then you have your reheat coil. And then down in the center, you have your condenser coil in, not going to describe that color. So I'm bad at describing colors. Anyway, so let's focus on our hot gas reheat system. This is the refrigerant that leaves the compressor and then travels to our reheat coil and condenser coil. So starting off, our hot gas leaves the compressor. It then travels to a three-way reheat valve. Next, we have two paths that this hot gas reheat can travel. Path number one is through our reheat coil, and then the condenser coil is in series. Or path number two is it just travels to the condensing coil. So here's path number one. It goes through our reheat coil and then down through the condenser down below. Path number two is leaving the three-way valve in a different port. It then travels to our condenser. Now just note that in both this situation here for series hot gas reheat is that the energy is always being transferred in your condenser coil, all right? So now the difficulty with always transferring energy in your condenser coil, number one is you're going to shortchange the amount of heat transfer that is going to occur in your hot gas reheat coil. Different way to explain this is looking at a pressure enthalpy chart. Once again, I'm pretty sure everybody's familiar with these, but just reviewing quickly, from point 1 to point 2, you have your evaporator. This is where the refrigerant boils off. Compressor from 2 to 3. Your condensing is from 3 to 4, and then you have a completing the cycle. You have an expansion device, whether this is a thermal or electronic expansion device. So your cooling coil is from point 1 to point 2. This is removing heat from the air and then discharging it or entering it into your refrigeration system. And then you're from 3 to 4, you have your condensing where you're rejecting heat that has been picked up in the cooling coil, as well as in your, from your compression in your compressor. So depicting the two coils in series, first your hot gas goes to your reheat coil, and then second, it must travel to your condensing coil. So once again, you can see that your hot gas reheat coil has been shortchanged on the amount of heat that is available for reheating. The second part that you must realize is that you always have to maintain a head pressure differential between your evaporating temperature and your condensing temperature. This is depicted here between the two. This is for your refrigeration cycle so that your compressor can still operate as a pump. You typically do this by slowing your condenser fan speed to limit the amount of heat transfer in your condenser coil. So that's series. Now we're going to look at parallel. Once again, we have the same airflow where we have your space temperature entering your blue evaporator coil. Again, gets cooled and then hits your reheat coil. Once again, want you to look at the piping arrangement on the discharge side of your compressor where the reheat is. All right, so same again, your hot gas reheat leaves your compressor and it travels to the three-way reheat control valve. That valve is usually modulating. There's a little modulating there. I can't really see it too good. And then path one is your hot gas reheat can travel to your reheat coil, or path number two, it can travel to your condenser coil. Once again, this is depicted by leaving one port on the hot gas reheat valve. It then travels to your reheat and then travels back, bypassing the condenser. And then section two, or path number two, is leaving a different port on your hot gas reheat valve and traveling to condenser, and then back to your liquid line receiver, upstream of your expansion valve. So with this arrangement here, what ends up happening is that I have the ability to have more reheat output available. I don't have to discharge some of that reheat through your condenser coil. And then you will end up getting more accurate capacity control with this arrangement here. So manufacturers are transitioning from series to parallel hot gas reheat. As I mentioned before, you'll have better, more capacity available, better capacity control at part load conditions. You'll be able to achieve higher than nutrient layer leaving air temperatures for those grow rooms in indoor agriculture. And then more accurate capacity control can be done by using both refrigeration circuits. So for circuit A, we'll use this for your cooling and dehumidification leaving air temp by modulating the compressor. And then circuit B will be used to modulate the amount of reheat. We'll be doing that by modulating the compressor as well as a three-way valve. So back to our psychometric chart here, just showing the process. So circuit A is used to modulate the leaving air temperature from your for cooling and dehumidification, and then circuit B is used for your reheat capacity. Other items available on your DX system is you can provide draw-through or blow-through arrangement. Here's a picture of a draw-through where I've highlighted just your DX coil is upstream of your supply fan. This arrangement is obviously much more common. The benefit of this arrangement is that fan motors provide a little bit of reheat that ends up helping with condensation issues downstream of your cooling coil, ends up getting your leaving air temperature a little bit further away from your saturated, your 100% saturated line. Option for final filters, downstream of your gas heat. Just want to point out that these filters are usually specially made just to accept the higher leaving air temperatures that could be associated with gas heat. Now, difference with the blow-through is I've swapped the supply fan and DX coil position. You can see that the supply fan is upstream of the DX coil. Just previously it was downstream, just seeing this here. As I mentioned before, the supply fan being a little bit further away from the supplier opening could become a little bit quieter. With this arrangement here, you would have lower leaving air temperatures just because you are not picking up that fan reheat. And then just as I mentioned earlier, just this arrangement here makes the refrigeration system as one piece coming from the factory, so you don't have to field, connect, and charge two large pieces of a rooftop unit in the field. Other items, just quickly, duct connections available for supply and return, side, bottom, top. I know side connections are often problematic for rooftop units. Just the gas heaters, once again, generalizing, the manufacturers are providing higher output capacities, higher temperature rises, and then with greater turn down ratios. Filtration, they have two different types or two different locations on the inlet where you're upstream of your system and final is downstream. Inlet, you can get pre and final filters with all those different types and MERV ratings available. And then downstream, you can get, once again, all these different types as well as HEPA filters. All right, last 10 slides here or so. Let's go through AAON's option boxes. This is something that they've been providing on their large rooftop units since the late 90s. So this is a standard option that comes from the factory. It's an empty plenum box that is in the airstream. It could come with and without drain pans. They have these different lengths available. You can get one or two in your unit, and then they're available in 5 different locations. What requests that I thought up to come to use or provide with these would be to provide a humidifier manifold as well as your generator, alternate energy recovery devices with a plate heat exchanger, no cross-contamination with the runaround loop or your heat pipe, backup heating and cooling systems with the redundancy. We'll talk about that and how you already have that built in with your fan arrays. And then these option boxes, once again, could have sound attenuators or zone dampers or auxiliary filters in terms of like electronic filters, et cetera, like that. First, looking at humidifiers, HC&I represents Carrel. Just want to point out that we're not the Carrel rep in Delaware, that's BSS. For humidifiers, there's 2 main components. There's humidifier manifold or the grid, and then the actual humidifier generator that could be used with electric or steam energy. So here's a picture of Carrel's Ulti-SAM manifold. They do, like all manufacturers, they do have very short absorption distance from 9 inches to 24 inches up to 48 inches available with these large capacities. In terms of flexibility, the supply steam to these manifolds can be fed from the top or the bottom. And then just being an old-timer salesperson, do like the fact that you can select these units with a computer selection program, to help me, convert the pounds per hour and grains, et cetera, like that I'm rusty on. All right. So our manifold, let's talk about where these can be located. This is a cutaway view of the rooftop unit. From left to right, you have your supply air, you have a gas heater, your fan, DX coil. On your inlet, you have your outside air, return air connections, as well as your filter. Location A can be downstream of your heating coil here. And then location B could be upstream of a hydronic preheat coil. And then, location B has the other benefit of that it's downstream of a chill water DX coil. I know a lot of engineers like to consider that DX or that cooling coil as sort of a moisture eliminator, so that you don't have to worry about air that's been humidified that goes beyond its saturated suction, and then you have actually not mist but water traveling downstream to your components. In terms of the generator, once again from Carrel, they have 2 different electric types. The smaller one is Humidisteam. This is the ones with, on the right, the disposable canister. These are used for potable water Always get confused which one to use for that. And then a little bit larger size is a heat or steam model, where instead of having the canister, they have the electric resistance heater that's shown on the right. It's not bigger than the actual cabinet. And then just has a little bit higher or a little bit more flexible in terms of your water type that can be used. These two are electric. Corel also has a gas-fired one. These gas-fired ones come with much larger capacities. Once again, these different water types. And then the other thing that's nice about the gas-fired is that they do recently, they do have a outdoor weatherproof enclosure that is available. As you can imagine, a 1,000-pound steam generator can get pretty large. Next, we're going to talk about energy recovery. Just a quick refresher in ASHRAE 90.1 2006. There's a chart about when you are required to use energy recovery. This chart, there's two of them. This chart here is based on 8,000 hours per year. 8,000 hours turns into 22 hours per day. They have the chart based on the left is climate zone. The area or the territory that HC9 serves is typically 4A and 5A. And then on the center on the right, they have charts that explains or just depicts the amount of supply air CFM that is used versus the percentage of outside air. As you can see, as you go from left to right, the outside air, as you increase the percentage of outside air, the threshold of your supply air reduces. So just if you have a unit with 20% or less outside air, if your supply air is greater than 26,000 CFM, you have to employ a energy recovery device. If that same unit had 50% outside air for your design, you can see that between 40 and 50%, your supply air threshold is only 4,500, where you would be required to provide an energy recovery device. Once again, this is I believe, or this is a review that you guys have seen, plenty and plenty of times. All right. So energy recovery most commonly used is a. This can be also, or the matrix itself can be polymer or aluminum. There's 4 different sizes available. It's available up to about 36,000 CFM. That's maybe about 50% of your total supply air for these RZ units. You do have an economizer, a bypass available for economizer operation. Here's just a side view of that energy recovery. Just want to point out that the CFM limitations are really based on, you have 2 air streams that have to fit in one cabinet. So that's the reason why you can't do 100% outside air up to 80,000 CFM in these large rooftop units. Next is the plate. Once again, everybody's familiar with these. They come as sensible only or total. There is a bypass available. Here's a side view of a unit with a plate. Once again, your CFM is limited just because you have 2 air streams in one cabinet. And then the other thing I just want to point out versus the previous slide is that with this arrangement here, you have your return air on your lower left and then your outside air on your lower right. On your lower right, just be careful about your outside air intake, about where it's located, how high off the ground, et cetera, for snow, grass, et cetera, like that. Just be careful about that. Maybe you have to install a larger roof curb, underneath the unit. Other options for energy recovery are runaround loop. Once again, this is nothing new. You have 2 air streams with coils in it. You have hydronic piping. Typically, this is glycol. You have a circulating pump with controls, pump trim, etc., like that. This is sensible only. There's no cross contamination. Here's the location in the unit. This would be in the option box. The thing that's nice about this option is that you do have larger CFMs available because you're only have one coil in one airstream versus a previous slide showing 2 airstreams for your energy recovery. Next, instead of hydronic, you have refrigerant-based. Once again, this is sensible only. You have your two airstreams with refrigerant piping connecting between them. Once again, similar to the hydronic, you could achieve larger CFMs based on your one coil and one airstream ratio. So the two options for without cross-contamination are runaround loops and heat pipes. HC&I represents heat pipe technologies. There's their website. Tampa, Florida. Maybe that should be Tampa Bay. I always call Tampa, Florida, Tampa Bay for whatever reason. Anyway, they've been around since 1983, and then their coils are AHRI certified for performance. Just the runaround loop is available with 8 different systems. Once again, benefit using heat pipe is that it's pre-engineered. You can get the pump skid with the controls all prefabricated, available to those sizes. And then with the heat pipe, these are available up to 120 feet physical distance separated between them. They're available with side-by-side as well as top-bottom orientation. Last thing to talk about with these option boxes are backup redundancy. This might be used a lot in the healthcare industry. I remember working on a project where they had, a hospital had to store some chemo chemicals and et cetera like that. So they required 2 systems for backup. Just on the standard unit, these units have a fan array. So they have, from an airflow perspective, you can get those as N+1, so they have redundancy built in. With these option boxes, from a heating perspective, let's install a second coil. As shown there, these can be electric, hot water, or steam. From a cooling perspective, we can have chilled water, or else we can also have a DX. AEON makes a remote condenser available up to 230 tons that could be paired with your rooftop unit for redundancy. All right, so today's summary, we went over application considerations for best practices. We went through ductwork and weight, spent a lot of time talking about sound and vibration. Next, we talked about the direction that the industry is taking in terms of refrigeration components with your VFD compressors and your parallel hot gas reheat. Gas heating filtration, once again, is following the same path as the other devices, just more options, better components. Draw-through versus blow-through configuration. And then lastly, we went through the custom option boxes with humidification that was available, the different energy recovery options, as well as the ability to provide backup and redundancy. So just a shout out to AEON, their new RZ series. This is their 3rd generation. It went from the early 90s. It's available from 45 to 240 tons with those airflows. It currently is air-cooled on the condenser. In a short time, they're going to come out with water-cooled, as well as heat pump, as well as evaporative. All the units have a service vestibule. There's 3 levels of filtration, all the way up to HEPA filters. The supply fan, return fan, exhaust fan are available as fan arrays, minimum of 2, up to 9 or 12, depending on your size. They do have an option for permanent magnet motors versus your traditional induction type. Energy recovery options that we talked about, as well as the heating with gas, electric, steam, as well as hot water. And then once again, HVAC in a box, once again, your controls and your sequence of operation are all contained in the rooftop unit. Great for quick turnaround and flexibility, and not having a lot of field installed components that have to be worked, programmed and tied in and troubleshooted in the field altogether. All right, just what we have coming up next for our webinar series, topic in a month from today, once again on a Tuesday. We're going to talk about filtration, / indoor air quality. Just broad brush of what we're going to cover. Still working this out. First, we'll review the once again basics of filtration as well as indoor air quality. We'll review the applicable codes. We'll probably go back again and see if there's any updates to the epidemic task force that ASHRAE has issued in the last year. And then just once again try to not just give you the basics, but then how you can actually apply these improvement in filtration with these products that AAON has available. All right, so here's my last super duper last slide. We're also having a kitchen design seminar on April 20th. Had a great turnout for part one. This will be by Jeremy. Once again, reminder that we have 1.0 PDH credits available. And then once again, thank you all for attending. Hope these webinars and seminars are worth your time. All right, at this time, let's start going through the questions.
All right. Why was series high-class reheat the norm? Were there technical issues parallel difficult? That's from Pete Honeyford.
I think the answer to that is probably from a initially from a installation standpoint, it was cheaper to do it that way. The other thing that has to be considered or just transitioned to is that there's so many different components and systems available with hot gas reheat in terms of the compressors, whether they're on-off or now two-stage digital scroll VFDs, different coil components, aluminum, copper, as well as aluminum microchannel, as well as the controls, et cetera, like that. So kind of to answer your question, I don't know exactly, but I would presume that it was a cost and design perspective. It's easier to implement it that way.
Jim, if I could here, one of the main reasons that they're switching, and they haven't done this across the board yet, but the parallel reheat will give you more reheat capacity, and we're seeing this as a driver in grow room applications. With the series reheat, you're limited to about coming off the coil at 74, 75. With the parallel reheat, you can actually get up to about 99 degrees leaving air temperature off the hot gas reheat coil. So I hope that helps explain to you a little bit, Pete. But we can dig into that and get you a more suitable answer. Next, can you restate the name of the Paragon 3-in-1 controller available? That is the multi-trans ecosystem.
Yeah, I can go back to that slide. Could have done this faster.
I can email out to you a copy of that tear sheet.
There it is. after 50 clicks. Multi-trans smart ecosystem. Bam.
Yep. Okay, Robert Mulrooney. I think the EU requires by code that an energy recovery device has an inlet filter, such as a plate heat exchanger. Would this be pretty typical for these RZ series units? Yeah, we would have to have a filter prior to hitting the heat exchanger on the outside air. So,
right there it is depicted there. And then a lot of times, it's in the upper right in the elevation view, and then a lot of times we also put a filter on the return air side, even though the air in the space has been kind of filtered already.
Okay, is there an option to have internal spring isolators on the fans? Yes, the RZ series has spring isolators on the fans. And there was a question that was posted in the chat. If the RTU is split into two pieces, can we still maintain one electrical point of connection? And the answer is yes. It is still single point power. There would be an interconnecting wire module between the two sections that the contractor would have to connect in the field.
Right, as well as for controls, there would be plugs.
And that's all the questions we have for today. So once again, we are recording this webinar. It will be posted on our YouTube page under HC&I Company. We appreciate everyone taking the time out to join us today, and we look forward to having the opportunity to work with you soon. Jim, thanks again. Did a great job.
Thank you. Thanks, Buck.
Everyone have a great week.
Thanks again.